Welcome everyone to this presentation. So like mentioned, it will be about incident response planning using a lightweight large language model with reduced hallucination. And my name is Kim, and this is joint work together with Tansu and Emil. So we consider a general incident response use case that involves an IT infrastructure of some organization. And this infrastructure consists of a set of interconnected components, some of which have been compromised by an attacker. And the problem is to design a response strategy that uses observations from the system to automatically prescribe effective response actions for recovering the system. And those actions can then be used as decision support or as recommendations to a security operator. Now, conceptually, you can think about this problem as a form of a control problem, where we have some internal system state, X, that describes the nature of the incident. And once we have detected the incident through the observations, we want to select a sequence of actions that drives the system to a secure and operational state as quickly as possible. And the way that this problem is currently being managed in industry and traditionally is through so-called security operation centers, where you have human operators that sit around the clock and analyze security alerts and try to figure out how to effectively respond. And while this approach can be very effective, especially when you have skilled operators, it is also very costly. And many studies indicate that we have a huge global shortage of these operators. So there is a very strong demand for new decision support systems that can reduce the workload on these operators and help them to do their job more effectively. And one promising approach to build such systems is to leverage the vast knowledge that is available in large language models. And in fact, this is an extremely active area of research and development where just in the last year, all of the major IT vendors have released some form of an LLM-based incident response system. And essentially how these systems work is that you prompt the LLM with details about your incident, and then you simply instruct it to generate a recommendation for how to respond. And surprisingly, this actually works quite well in practice, and especially works a lot better than traditional incident response playbooks in many ways. But from an engineering point of view, so I come from electrical engineering, it has a lot of fundamental limitations, this approach. And one of the main limitations is that all of the existing systems are based on external LLM providers. So they require you to send potentially sensitive information about your incident to Google or OpenAI in order to generate the response. And the second major limitation is that they are inherently unreliable. So they have no theoretical guarantees whatsoever. And most of the existing systems are also based on general purpose LLMs. They are not specialized for incident response. That makes them particularly prone to hallucinations. So in this work, we address these limitations by presenting a method for incident response planning with an LLM, which is lightweight, has theoretical performance guarantees, and reduces the risk for hallucinations. So from an architectural point of view, the method consists of three main steps, as illustrated in the figure here, where first we fine-tune a lightweight model based on a prior data set of incidents and responses. And then we integrate that model into an online planning algorithm where we combine information retrieval with a form of lookahead optimization. And we prove in the paper that this approach allows us to provide certain theoretical performance guarantees and also to reduce the risk of hallucinations. So the way we do fine-tuning is simply that we take details about some incident from this data set that we have, feed that through the model, and via chain of thought prompting, we instruct it to generate a response action. And then we simply compare the generated action against the ground truth that we have in the data set. And we do that comparison by taking the cross-entropy loss. Then we take the gradient of that loss, and we use the gradient to update the weights of the model using a standard gradient descent. So this is quite straightforward supervised instruction fine-tuning. And really the main challenge here to do this in practice is to obtain the data set, to obtain a representative data set for incident response. So we have spent a lot of time in assembling such a data set that consists of 68,000 incidents that covers a broad range of different types of systems and different types of attacker tactics. And to our knowledge, this is the first publicly available data sets for fine-tuning incident response. And in principle, you can use this data set to fine-tune any model of your choice. But for the results that we report in the paper, we used the DeepSeek R1 LLM. And we use a version of this LLM that has 14 billion parameters. So this is a very lightweight model if you compare it to the frontier. And in this figure here, you can see the convergence of the loss during fine-tuning. And what we find is essentially that we can fine-tune this LLM in about 8 hours on a commodity GPU. So it's a very cheap fine-tuning process that I think any organization could be able to do. The second step of our method is then the information retrieval step, which has a very simple motivation. And that is that there's always going to be a gap between the time where we fine-tune the model and the time where we're actually going to do the planning. So for example, if we fine-tuned the model, say 2 months ago, then the model would have no way of knowing about some vulnerability that was discovered last week. So for that reason, before we do the actual planning, we make sure that we retrieve all of the relevant information about the incident from external sources, like open threat intelligence APIs, for example. And then we simply incorporate all of that information into the context of the model before we do the planning. And then to the actual planning, which is illustrated here. So this is a quite a little bit involved method with all the details available in the paper. But the main innovation is that during each stage of planning, instead of just generating a single response action, we generate n different response actions, where n is a configuration parameter. And for each of those generated actions, we do a form of lookahead evaluation, where we evaluate, okay, if we take this action, what is the expected impact on the system in terms of the service availability and in terms of how we will get closer towards recovering from the incident. And then we simply pick the action that, according to the look ahead, leads to the shortest or quickest recovery from the incident. And we prove in the paper that by doing that, we are able to essentially control the hallucination risk by increasing the number of candidate actions. So to be a little bit more precise, the way that we define an hallucination in this context is that we say that an action is hallucinated if it does not make any progress towards recovering from the incident. So for example, if you would have an action that aims to patch a vulnerability that doesn't exist, that will not make any progress towards recovery, and that will be a clear hallucination according to our definition. And the first basic result that we present is that once you have fine-tuned the model, you can do some simple offline tests where you just empirically verify how frequently does the model hallucinate. And then once you have that empirical estimate of the hallucination risk, you can then obtain the standard Chernoff bound on the actual hallucination probability. And that provides an important insight for our method, which is illustrated in the right plot there, which essentially shows that even if you have a very high hallucination probability of your model, as long as you have enough of these candidate actions, you can be very certain that at least one of those actions is not going to be hallucinated. And that turns out to be very important for our method because of the second result that we prove, which is that as long as one of the candidate actions is not hallucinated, then our method is able to filter out the hallucinations and actually pick the one that is not hallucinated under certain regularity conditions. So that essentially provides a theoretical performance guarantee of our method and also some insight for the operator about what is actually the risk of using this system in practice. We have also done an experimental evaluation of the method where we applied it to 4 public datasets of incidents reported in the literature. So all of these datasets consist of PCAP files and security alerts and so forth related to different incidents. And the way we evaluate our method is essentially that we prompt our method with these details about the incident, use it to generate a response plan, and then we compare it against the ground truth. And we also compare it to have some baselines to compare with, we also compare it to the frontier models. So I did this experiment like 6 months ago, and then at that time, these were the frontier models. So DeepSeek R1, Gemini 2.5, and OpenAI O3. And of course, the main difference between our method and these baselines is that our method is very lightweight. So I run this on a very simple commodity GPU in our office, whereas to run the frontier models, you would need probably a whole data center. So it's a very huge difference in cost of these methods. And here's a summary of the evaluation results, where we look at 3 different metrics. So we have the recovery time, the percentage of ineffective actions, and the percentage of failed recoveries. And you want to keep all of these metrics as low as possible. And the performance of our method is shown in the red bars. So you see the average performance in the top row. And what we can notice is that our method outperforms the frontier models across all evaluation data sets and across all evaluation metrics. And if you look among the frontier models, we find that Gemini performs best on average, whereas the difference between DeepSeek and OpenAI in this particular evaluation is not really statistically significant. They are more or less equally good. And now, of course, the question is, what is it that drives the performance of our method? So why is it better than the frontier models in this case? And to answer that, we conducted an ablation study where we evaluated our method with and without each component or each step. So the first row is with and without information retrieval. The second row is with and without the fine-tuning. And the third row is with and without the planning algorithm. And what we can see is that all of these 3 steps contribute positively to performance. So if you remove any step, the performance degrades a bit. But the degree of this degradation varies quite a lot between the different steps. And in particular, we find that information retrieval has a very minor impact on performance in this case, whereas fine-tuning and planning has quite significant impacts on performance. So those are the main drivers to why our method outperforms the frontier models in this experiment. Now, in terms of computational cost, there is a certain expense of using our method in the sense that it has to invoke the LLM many times to generate a response plan and do this lookahead optimization. And the number of invocations scales linearly with the number of candidate actions. But the good news is that you can do this evaluation in parallel on different GPUs. So the more GPUs you have, the more actions you can evaluate within the same time frame. So in that sense, our method is horizontally scalable. So in conclusion, it's very clear, at least to me, that LLMs will play some role in security operations. But in my opinion, the degree of that role will really depend on how we will be able to manage the hallucination risk and how we will be able to build reliable systems from unreliable components. And in this work, we have presented a method, a novel method for incident response planning, which is reliable, lightweight, has theoretical performance guarantees, and significantly outperforms the frontier models on the evaluation scenarios we considered. Thank you very much for your attention.
Thank you. Any questions for our speaker? Please just form a line here. That's fine.
Hi, my name is Dr. Alicia Carey. I'm from Walmart Security Operations. So I'm just wondering, have you thought about how this will scale? Because Walmart is very messy and our infrastructure, it's, as you can imagine, we have a lot of it. So I'm just wondering if you've thought about how you could take this from, just using it on toy data to scaling it towards actual implementation.
Yeah, that's a very good question. So I have a background like doing a lot of reinforcement learning and decision theory for incident response in the past, and those methods definitely do not scale. That's a key challenge with them. But I would actually argue that this method scales very well. It is actually surprisingly general. So we find that we can use this method for a very broad range of incidents, and it just works very well. And you don't really need to fine-tune it for particular incidents, particular incident types. It's already very general and can scale to quite broad set of incidents. And in terms of scalability of the operational cost, of the computational cost, that was shown in the previous slide. There's a certain cost there, but I think since the model is lightweight and you only really need a couple of commodity GPUs, it scales quite well in there as well.
Thank you.
Thank you.
Hi, Francis Hahn, University of South Florida. Can you briefly summarize your proofing method?
Yeah, so the first result about churn of bound, that's really just, it's very straightforward proof. We just basically applied the existing bound to our particular use case. We have shown that the samples from the LLM are, if they are IID, essentially, then we can invoke the bound. For the second result, then we have a very elaborate proof, and that proof essentially boils down to, so we formulate the incident response problem as a stochastic shortest path problem, and then it's basically a specialized form of Markov decision process, and then it's just about bounding the difference between the actual unknown Markov decision process and the Markov decision process we get when we're using the LLM to do the lookaheads. And we basically put a parameter to the difference between those two models, and then we can basically propagate the bound from that.
Okay. And did you compare these to any like a human evaluations, like for analysts or anything like that?
No, that was the main thing the reviewers asked for. Actually, we would love to do that, but we didn't have the capability to do that. But it's something we plan to do in the future, like to get in collaboration with industry.
Cool. Thank you.
Thank you.
Vinny Adibi, PhD from Georgia Tech. So I have two questions. The first one, how did you handle the context length of the models? Because I assume if you are passing like pickups, that's a lot of data.
Yeah, that's a good question. So we actually pre-processed the data a little bit. We didn't pass the raw PCAP files. We ran the PCAP files through Snort, and then we just passed the Snort alerts to the model. And in that case, we never actually had any issues with context length. So the context length of the DeepSeek model we used was 128K. And we find that in all cases, we were way below that. I mean, it was like maybe 20K tokens or something like that. So we didn't really run into that problem, but I still definitely acknowledge that in practice, when you have much more data, this could become a problem. And then I think you will need to use some kind of context compaction techniques. Maybe you compact your data and summarize it in some way before you pass it to the model in order to manage that. But we didn't do that in this paper.
Okay. The second question, in one of your experiments, you said that when you do RAG, it does not really influence the outcome of the model. And given that you use past data sets that do not really need any new information, do you think that might be a reason why you did not see any improvements with RAG in your experiment?
Yeah, that's exactly the reason. We mentioned that in the paper as well. I just tried to be brief for the discussion, but that is actually the reason that, or we speculated that is the reason, because all of the incidents we considered, the attack techniques are quite well known. So it's likely the model has seen something similar during pre-training, and therefore information retrieval is less useful in this particular evaluation. But we still think that it could be useful in practice when you have really 0 days or unknown vulnerabilities or very recent vulnerabilities, and then the information retrieval may turn out to be very useful. But for this particular evaluation, like your intuition is correct, I think.
Okay. Follow up to that, did you by any chance just try if it works in like things nobody actually ever experienced before, like new attacks, new?
No, we didn't actually evaluate. We applied it also, I didn't show that evaluation, but we applied it also just like a standard benchmark in the community for incident response, like a simulator. We applied it to that as well, and there it also achieved very good performance. But that is also, it's not a real attack, so it's not really, but it's an unknown simulated attack. So.
All right, thank you very much.
Thank you.
Hi, Florian Handke from CISPA. Thank you for this interesting talk. Maybe I missed it, but what I would be interested in is how exactly the plans and responses from your model look like. Would it be something like shut down server A or shut down server B? And if so, how do you handle dependencies you would need to shut down server A before shutting down server B, or things like that?
Yeah, so good. Let me start with the format of the response plan. So that is basically a textual format, like a sequence of actions. And they are very similar to incident response playbooks in that sense that it's like text and it's related to MITRE tactics and so on. They classify the actions and so forth. But the main difference is that the actions are much more concrete than what you find in a playbook. Usually the actions include actual commands on the system, like specific commands to run. So that's the format. And then about the constraints, in this work we did not consider it. But we do actually have ongoing work now and some future work where we are looking into that, where you can have like a feedback loop where you generate a response plan, and then you can actually verify it formally against certain constraints and give the model feedback, and it can update the plan through in-context learning. But we didn't do that in this particular work.
Okay, cool. Thank you.
Thank you.
Hello, great talk. This is Jason from Microsoft. I have a question about I'm curious about I think in your system, you assume all the knowledge or the threat intelligence are all provided. I'm curious whether you have measured your systems, for example, if the threat intelligence, because sometimes it's limited or the logs, some are not updated, up to date. So what kind of performance in your system, whether the hallucination or the accuracy or any metrics, have you check what's the difference if the knowledge and the threat intelligence are not provided accurately?
Yeah, so we didn't do a specific evaluation on that particular problem, but I can say that in the evaluation we did, we tried to make sure that the information we give to the model is more or less the same that an operator would have in a SOC. So it basically is you just know about the topology of your system and roughly what services they run, and then you have a few very vague alerts that does not give the full incident picture at all. It's just very vague alerts from Snort, and then the model has to figure out based on that how to generate a response. So they have partial information in all of the evaluation incidents, but we didn't particularly measure if we change how much information, how does the performance degrade. We didn't do that measurement, unfortunately, yet.
Okay, thank you.
Yeah.
Kamala Kaya, I'm from Virginia Commonwealth University. I wonder about your incident response data set. You mentioned that you are just assuming a set of instructions, technical instructions. Do that include organizational level decision making? Because in incident response, it's not just about taking actions, but also, with regards to compliance, you need to let some parties know about the situation. Assume a ransomware attack, there are a lot of non-technical decision making. I wonder if your data set includes those, and if not, how do you think that the LLM would be successful there? I mean, what is your thoughts on that?
Yeah, that's a very good point. And I agree that in practice, in response, there are many actions that are not direct commands on the system. And I think most of that is left for future work. But what I can say is that in our data set, we include 6 types of actions. I think it's containment, eviction, then there's also assessment, and that is not so, that can be more general actions also that you should call in a particular forensics team sometimes. That is the right action to take and not directly technical. And then we also have restoration and hardening actions. But I think there are much more you can include there about organizational policies and different things. But in our current data set, we don't include that. But I think that's a very promising direction to include much more. The more structure we can include and the more things that we can actually have constraints on how the plan should look like, I think the better this will work. Because then you get this feedback loop where you can essentially, even if the model makes a mistake, you can force it to comply with certain things and it can get better. But that's mostly left for future work.
But do you have access to that data set that will include organizational level decision making?
No, not currently. We just have our own data set, and that includes some degree of that, but not the full degree. And that is available on Hugging Face. Yeah. Thank you.
Any more questions?
I have a super quick one. Sorry. Hi, pleased to meet you. Simone Onso from Eurecom Research Institute. Thanks for the talk. A super quick question about why did you use DeepSeek only, or did you try the other LLMs, or what was the decision making in order to choose DeepSeek?
Yeah, so this was mostly that. So we did this like 6 months ago or something. At that time, the number of models were a bit less, and also basically the choice was just I had a GPU and I wanted to use the most powerful model I could fit on that GPU essentially, and that was a 14 billion parameter model. And if you then constrain to 14 billion parameters, there was only DeepSeek and maybe Llama or one more. There was not that many, and we just chose DeepSeek. So I think an interesting evaluation for future work is to compare with different models, but we didn't do that.
Okay, thanks.
Yeah, thank you.
All righty. Well, our speaker is available. This is a short session since we have 3 papers, but let's thank our speaker once more.